Electrons in iron are spinning. Now, on a piece of iron like this, the electrons are spinning all different directions. But in a magnet that's made of iron, the electrons are all lined up, so that a magnet has a front end and a back end, a north pole and a south pole. Now, what would happen if you could cut a magnet in half? Would you get a magnet that was only a north pole or a magnet that was only a south pole? Well, take a look at this. These are the electron cars of science, and they each have a front end and a back end, a north end and a south end. Now, right now, they're parked all which way, but let's line them up like the electrons in a magnet. Back it up, Joe. Okay, Sally. There. Now, let's cut them in half. See, we end up with two smaller magnets. These cars have a north end and a south end, a north pole and a south pole. So if you break a magnet in half, you get two smaller magnets that each have a north pole and a south pole. Near as we can tell, there's no way to get a magnet with just one pole.
When a bunch of magnetic atoms get together to make a solid, they generally have two options. One is for all the atoms to align their magnetic fields with each other, or they can align their magnetic fields in an alternating fashion so they all cancel out. The atoms will do whichever one requires less energy.
That's why chromium, for example, is a very magnetic atom but a very unmagnetic solid, because it's one of the most anti-ferromagnetic materials that we know. Iron, on the other hand, is the namesake of ferromagnetism, so it is unsurprisingly ferromagnetic, or, in usual parlance, magnetic.
Sometimes. The last and final level of magnetism is that of domains. Essentially, even in a magnetic material where the magnetic fields of atoms line up together, it's possible that one chunk of the material will have all its atoms lined up pointing one way, and another chunk will have all its atoms pointing another way, and so on.
If all of these domains are of a similar size, then none may be strong enough to force the others to align with it. In which case, a piece of iron, for example, may have no magnetic field at all because of all the warring magnetic kingdoms within it.
However, if you apply a strong enough magnetic field from outside the material, you can help one domain expand its control over its neighbors, and so on, until all of the domains have been unified into one kingdom, all pointing in the same direction.
And now, finally, you can rule with an iron fist! I mean, magnet. It's magnetic because it's ferromagnetic and all of the domains are aligned.
Exactly. What's remarkable?
Let's think about what we've learned so far. Materials which can be magnetized, either becoming a magnet or being attracted to a magnet, are called ferromagnetic materials: iron, nickel, and cobalt. Here we see two random pieces of iron. On the left, over here, this would be something like an iron skillet, just a random piece of iron. It's not a magnet. It, however, can be attracted to a magnet. Now, if I want to make that piece of just normal, regular iron into a magnet, what I need to do is get those little tiny magnets inside of it to line up. So if you look at the one on the right, see how all the magnets are lined up in the same direction? So our magnetic domains are all working together in the same direction, so that this whole side is a south pole and this whole side is a north pole. Here's another way of showing it with arrows instead of showing the tiny magnets. So think of the front of the arrow as the north pole and the back of the arrow as the south pole. What do you think about picture A? Is picture A a magnet or just a normal piece of iron? If you said normal piece of iron, you're right. Because the domains are random, pointing in every which direction, that's just a normal chunk of metal. It might be attracted to a magnet, but it is not a magnet in itself. Go ahead and look at B. Do you think that's a magnet? Sure is. That's a strong magnet. Look how all the domains are lined up. So we've got a north pole on one side, a south pole on the other. They're not in random directions. They're all pointing in the same direction. Look at C. Do you think that's a magnet? It sure is. So they're mostly lined up, mostly pointed in the same direction. But do you think letter C is going to be quite as strong of a magnet as B? No, probably not. Because in B, all of the little domains are perfectly lined up. That's going to be a strong magnet. If you look at C, the domains are not quite as lined up. That's going to be a weaker magnet.
Did you ever wonder which way is north? You could tell if you had a compass. They're easy to make. Just rub a needle with a magnet. Always rub in the same direction, like this. Rub it a lot, like 50 or 60 times. Now, put the needle on top of a film cap. It's plastic and it floats. The needle will slowly turn to point north. Science always points you in the right direction.
In the last video, you saw a girl turn an ordinary iron needle into a magnet. This is what was going on. So inside the needle, the domains were all in random directions. But as she rubbed it over and over in the same direction, notice how the domains start to line up. They start to point in the same direction. So she had to keep rubbing it and rubbing it. It took a while, but notice how they all point the same way. She has now created a magnet.